Alright, another relativity and lensing video, I guess. I don't want to waste too much more time on this, but it's interesting, and if I could find the argument that would make this conclusive, in the sense that if they would agree that if I can demonstrate the impossibility of what they're arguing, it would be advantageous to me. So it might be worth pursuing, because this paradox is really quite nonsense. Alright, now the real problem with what they're doing here is they're doing the traditional, like Einstein, the equality thing. I really hate this, that I can't remember terms. The fact that it's all the same. Gravity, the acceleration in an elevator, blah, blah, blah. You go through all these different things and you say that it's all the same thing in principle. Well, fundamentally it's not. So let's understand, okay, here's the Einstein crapola about the gravity well. So this goes to the lensing thing. So the thing falls into the well, travels a crooked line, flies out of the well, and goes straight again. And this distance is counted to be the straight line time. So it did the time the same as a straight line, but it obviously did this extra distance. Now what these guys are doing now here is they're taking this Einstein bed space thing and they're applying it to this velocity equation. And the real problem is they're adding the momentum. So let's understand that what happens when something falls into this gravity well. I guess I should have drawn it the other way. Yeah, well, anyway, it doesn't matter. You get the idea. It's extra distance. What they're saying is, okay, the light gets this extra momentum, and that's why this adds up, is because, well, it gets this extra momentum, and then it gives back the momentum here. So that's the conservation part that exists in this stupid well crap that's driving things going in and out of gravity, so their velocities don't change and all that stuff. It's accelerated and then accelerated out of the well without consequence. Because the momentum is given and the momentum is taken away by the bent space machine. Okay, it's not anything in the real universe, real energy. Here, they're giving it real energy. So they're saying, I'm giving the thing momentum. So the photon is going this way and this way, and that's their problem. They're giving the photon two momentums and having it travel. Now the problem is they gave it, so that's going down into the bent space of their time dimension. And my argument is well, if I put this hole in the ship and this light continues, where's the out of the gravity well? Where do you take the extra momentum away? And there's no place to take it away. So these frames of reference don't mean anything when you have something that is a constant, like light, go from one frame to the other frame. There can't be any more of this gameplay of where does the light convert? Where does it go? Out of the frame and then back into the new frame, or whatever it is, the frame and then the deeper frame, or the frame and the shallower frame. Where's the frame line in this experiment? Where's the place where you take away this extra momentum? Right here, or right after it goes through the hole, or right when it goes through the hole? What's the magic, arbitrary, I need it to go away, I need the momentum to go away, so I'll just arbitrarily say it goes away here. Right here it goes away. Magic. And now the light beam is just going the speed of light. Because right here it's not going the speed of light, it's in the bend. It's going faster than the speed of light, because it's going to get here, even though it bent, faster. So here's the bent space line. Where's the circumstance that tells the light you can't do this anymore? You can't do this supersonic speed shit anymore. You have to go back to being regular light again. Where's that point? And that's why it's not applicable. It is a true paradox in the sense the equations are broken. Paradox means broken. Unless you have an axiom, unless you have some axiom glue. So what are you going to do? Huygens? Heisenberg? Dark matter? Poppy space? The space knows there's a hole in the ship and there's going to be a paradox, so it says, get rid of that extra momentum. Magically. I'm just going to take it from you, magically. Because it wasn't real in the first place. You can't have non-real momentum. You can only have it in our synthetic thought experiment bullshit. So I'm just saying, there's no way around it. For it to go through a hole in the future, it has to take this line, and if it takes this line, it's going to travel faster than the speed of light, and if it goes through the hole, it's still going faster than the speed of light, and you can't fix that with this stupid mush by saying I have an equation. Well, your equation doesn't fix the physical paradox, the physical problem. And my argument would be your assumption that you can give light momentum is wrong. Einstein's gravity well doesn't exist. It's just a way of replacing the real force of gravity. The real force of gravity doesn't need to bend things to change their direction. So it doesn't have a problem with straight lines. The real force of gravity loves straight lines. It loves the idea of giving things two velocities. It does it all the time. It loves it. It loves pushing down while it's going another direction at the same time and mixing the two. So there's nothing wrong with a real force doing it. It's only when you create a fake dimension that all of a sudden you have to account for the fact that you are making longer lines. And the longer lines can't be rationally explained. Where you can explain two separate velocities having an effect on position. Alright. Well, velocities in the sense one is in the form of an acceleration. A constant acceleration. A constant effort to change the velocity. And failed in the case of something already moving. Yeah, it fails to accomplish the task of taking away the movement it already has. The direction, well, it does take away its direction. It forces it to do this constantly. It just keeps forcing it to do this, but it's still going. Yeah. Alright, I don't know if I need to say anything else on this. So yes, except you still haven't explained away the fact that look, even in the real world, take away the thought experiment, even the light from Venus. If you're going to argue the light from Venus has two momentums, alright, no matter how small the second momentum is, it just doesn't matter. You give it any second momentum, you're creating a hypotenuse, okay, and that hypotenuse is going to be longer than the side. So any second momentum you give anything, the baseball, any example I use in the physical world, if you give it extra momentum in another direction, you automatically increase its speed as long as the second momentum isn't in the opposite direction. So as long as the second momentum is in one of the other two dimensions, you have to increase the speed of the thing moving. The end point velocity will be some the net velocity will be larger than any of one of the arms. No doubt about it. And you haven't explained how that works in the real world. How light manages to do that in the real world. How the light from Venus falls out of. Where does it lose the momentum? You gave it to it. It's going as fast as Venus in a different direction than the photon emitted. So it has to be going faster than the speed of light. Alright. It just can't work. You can't give light momentum. And the only place you can hide it, as stated, is in a gravity well. By forcing it into a gravity well, then you can play your imaginary game, because then you can give it momentum and then you can take it away. but there's no takeaway in the rest of the real world. The rest of the real world, you release the light, and there's no taking the momentum you gave it away. There's no way to take its momentum away. There's no mechanism to take it away. There's no invisible Venus going the opposite way to push the light back and say, you can't be going this way. Or however to describe it. But you can't do it. It doesn't make any sense. Okay. So the lensing subject again. Oh, complications here. Alright, now, the first half of this video, I won't embarrass him. I won't embarrass him by... Here he's now applying Maxwell's equations. So Maxwell's equations are a derivative of Newton's equations to apply to the electromagnetic force, which it's one of the most famous huge numbers in physics. It has 30 zeros in it or something, 36 zeros as a power. Power to 36 zeros, 10 to the 36th. It's this preposterously huge number that represents the difference between the strength of the electromagnetic force and the force of gravity. And here he is applying Maxwell's equations to a gravity equation because he wants to find extra gravity. So anyway, so it's just wrong. Extremely wrong thing to do. so like I said, I won't embarrass him about it, but so he's trying to argue that these particles, like little charges, if you circle them, they add up to some grand amount and blah, 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 blah. And as I've been trying to point out, gravity is a density argument. To maximize gravity, you want to have as many protons, neutrons, and electrons compressed close to each other as possible. As little empty space as possible, and that'll give you more and more gravity. The more you spread them out, the less and less gravity you have at whatever circle you draw around them. It just gets weaker and weaker and weaker as you thin the percentage of electrons, protons, and neutrons. That's why the sun has so little gravity compared to the Earth based on its size, is because it has very sparsely separated neutrons, protons, and electrons, where the Earth has very closely compacted protons and electrons. It has heavy metals. The Earth has light gas. That's why the gravity created by the two things is very different for its size. The Earth is incredibly gravitationally powerful for its size. The Sun is incredibly gravitationally weak for its size. And galaxies are preposterously, for their size, they're as fluffy as fluff can get. Very, very extremely weak gravity. And again, this is high school physics or lower. You don't apply charge equations to gravity. That's just evil. Okay, so enough of that. So that part was just nonsense. Now, whether there's enough gravity to bend the light, has to bend light again, so we're back to something with a very high velocity. And so the thing I really wanted to, we had this argument, like I said, like 3 years ago or something, and I had to again point out the r squared problem. See, because you could think that, well, here I am, and I put a little dot next to where I am, and I'm going to go this straight line next to the dot. And so I'm going to go right close to the dot, get the gravity. Well, out here, I'm going to travel through more of it. So it'll balance out okay. But the problem is gravity spreads this way. So it's like the balloon getting really big, and you're not getting any bigger, and the little dots don't get any bigger. And you're just not be able to hit as many dots. So if the dots on the balloon don't get any, if the 100 dots on the balloon, they don't get any bigger, and you don't get any bigger, and the balloon expands, it's going to be hard to collect dots. You're going to have to go back and forth to collect dots, because the dots are spread all over the fucking place. They're very, very unlikely to get them easy. Like say if you're mowing grass, it's like you have to imagine that the territory you have to mow for every r squared implication grows by that 4, 9 16, 25 kind of, well, 20, 25 kind of way. Some other number in there. You know, so the area is getting huge. So there's no, you know, you plow in your straight line, yeah, you're cutting a little bit more grass because it's got wider, so you can cut the wider grass and you'll be okay. But the area of the grass has gotten huge. So you're not getting the job done. So the total job, that's the exposure to gravity, you're way short in terms of your exposure. Because the gravity's spreading, like I said, I guess the smart way to look at it is the straight line part is only one part of the equation. The other part of the equation is up and down. And so as you go further out, the up and down is the thing that's screwing you, is weakening your capacity to collect gravity. Because most of it went above you and below you. Okay, so enough of that. So the gravity, when I say it's weak, it's weak. That's theoretically correct. Okay, that what's happening is the gravity is spreading this way and this way as you get further away. So it's getting really, really nothing out here. Alright, so now we're back to the question of how much you need to actually bend the light enough, because your angles are getting so small. So he is correct in this later on when he goes to this argument that not to scale. So that when they draw these pictures, they're not to scale pictures, and that is important because the angles are fundamentally what we're talking about, but we're also talking about the great distances has a huge disadvantage. So the big advantage of the huge distances is that the angles get smaller, that you have to bend the light. But the huge disadvantage is the light has to travel through the universe. It has to travel through a whole bunch more crap. Okay, so you have to sort of think that if there's something 15 billion light years away and it's shining light at me, and it is, you have to that's the amazing part. The light's hitting me with a telescope, without a telescope. There's actual photons from the deep universe that are actually hitting me. 15 billion light years away, it actually does, and it comes right in here and it hits me. I just can't resolve it because there ain't enough of it hitting me. But it actually does hit me. Well, so the point is you think of it as a light bulb from its perspective, and it's just shining light on the entire universe. And so now when you see all the stars in the sky, you're saying, okay, that's just the ones I can see, you know. But just think of those as little black things that are in the way of the light you're trying to shine to somebody on the other side of the universe. And the light you're shining has to go through all of those little bits. Those little bits are in the way, and they're going to, some of them will completely absorb your photons, so those photons will go no further. And then, by their own theory, a lot of these photons are going to get bent around every single one of those stars. Alright? And they're going to get bent by a huge scatter pattern. So by the time my light's halfway away from me, just like the R-squared thing, just like the huge area of the grass to get cut, the photons themselves are separating by huge amounts of distance. So now the photons that are going to resolve me is a picture that's gigantic. I mean, it's hundreds of miles across. Okay, so an image of me that would be the size of this computer screen. Now think of this computer screen with its pixels spread out hundreds of miles. So I expand the picture of this hundreds of miles. You could see that the individual pixels end up being, 2 feet across, 3 feet, 4 feet separated. The individual little dots that are, they're in there. So those little individual dots. Well, they should be able to focus somewhere. Well, fuck it. Too many lenses. Anyway, those individual little dots start separating by feet and then miles. And so that's what's happening in space. So from that giant little flare in this galaxy 200 billion light years away, or whatever it is, 200 million. No, let's say 2 billion light years away. It's gigantic, right? I mean, it's hundreds of light years across, and that's how spread your pixels have now become. So just imagine that if those individual pixels are going through a different gravitational field, like this one pixel goes through a galaxy, this one doesn't. that one gets bent, this one doesn't. That there's no way you're going to be able to resolve them into an image. So I guess I would make an argument that if we accept the existence of lensing, then you have to explain how lensing doesn't destroy the light that's trying to get us to us from 15 billion years ago. You couldn't possibly see anything because the law of averages says the individual photons, because they're spread so far apart, would be annihilated before they got to us. They would be not annihilated, but they would be annihilated by the things that are solid. So everything solid they hit, they get annihilated by. So you keep filtering them out as they keep plowing into things, and you're weakening and weakening the light that way by plowing it into even just little tiny particles of dust will kill the light. So it's getting killed and killed and killed and killed and killed. Plus now you're saying that every time it goes close to a sun, it gets bent a little. And so that really is screwing it any chance that it's going to get to us as this image. It's just, when it finally reaches the destination, everything's going to be screwed up because the pixels aren't going to be resolvable anymore because they're going the wrong way. They're bent wrong. So they went way over there. The one I need, this little blue box thing, it went that way. So it's never coming back. Alright, so these are just physical problems that I don't think have been accounted for. Sort of paradoxes, I think. I haven't gone through all the math yet, so that's I'm gonna, the challenge is to see where in the math they make assumptions that get them in trouble. But even Einstein's math on the photon in the gravity well, I found a little bit hard to, it's not like I'm able to find errors in math, but it seems like there was some rigory there to make it make sense. But anyway, we'll see. As it should be pretty straightforward. I mean, the r squared thing is pretty straightforward. The amount of deflection per quanta is pretty straightforward. So once you establish a mass of a photon, it's pretty straightforward. It's just speed. Well, you don't even, like I said, you don't even need to establish mass. Once you establish the speed of a photon, the math should be pretty straightforward. About how much gravity per second it needs to encounter. So that's the number you're looking for, is the net amount of tug in one direction. Okay, anyway. So here, I like this. This has been to me somewhat informative, because this whole conversation, because these are things I hadn't thought of before, and just thinking about how much light we're actually radiating, because we're radiating light. Each bit of us that radiates light, like we're not reflecting light, we're radiating light, which I mean we aren't. The suns are. Sorry, these images. So they're really quite pure in the sense that they're radiating light in the traditional light bulb sense. That means they're covering the whole surface with these little LEDs. They're shaped like a bubble, and the light comes out in all directions from each tiny element of the surface. So it's radiating light like little light bulbs. So it's not dependent on reflection, where it could just be these little flat surfaces that are bouncing light and the other light's getting absorbed. I don't want to confuse things, but the point is you're radiating a ton of light, because you're radiating in all these directions that aren't going to land anywhere near this camera. I mean, that's the number I'm going to try to figure out, is what's the percentage of the light coming off of me that something like this little lens is actually picking up, which is tiny. I mean, the maximum amount of lumens, it's just a huge number of photons flying off of me. Insanely huge. So anyway, so you have these giant galaxies. So the real key thing is that the things they're looking at, that they claim are in the lensed objects, are as big as the lens in many cases. So when we talk about how far away they are, it's just understood that the lens and the thing it's lensing are, if you put them next to each other, somewhere comparable in size. It might be half the size, or this thing actually might be much bigger, but it's something like that. It's not a huge proportional change in size. It's a parallel, where the eyeball can never be parallel. So these lines will never be truly parallel. Now, the further I go away, this angle gets smaller and smaller and smaller, but it never parallels. So that's the one key. Now, the trick is the stuff getting lensed. Again, as stated, the lens is obviously this inverted lens. So it's not doing the traditional, what lenses often do, which is the crossover thing, And so it's doing, these lines are all straight. So the more parallel this line is, the top line, and then the light coming from the bottom would be the one that needs the high angle. So you could know one thing for certain, is that the image you're going to see won't be inverted. So this image doesn't get inverted. You're seeing the light on the inside of whatever's getting lensed, closer to the middle of the lens, is the light that's at the bottom of the thing, so to speak, relative to the place you're looking, the inside. And the lens from the other thing is the parallel. It's the one with the least gravity. So that's the only way the lens could possibly work. But the real point is that this distance, okay, when magnified by r squared rules, okay, this lens is really shaped badly. I mean, it's got this, well, that's not even the right way to shape it, because it doesn't have any roundness to it. It's an arc, and it's a severe arc of change. Lots of lensing here. No, I didn't draw it right. Something like that. That's not going to do it either, Gary. Well, anyway, the point is, the light here, very heavy gravity, but it needs it because it has to bend the light the most here, to get to the target. All right, because this line will never be parallel, and obviously going to this point will never be parallel. So that's what gives it away. That it has to be, if it did the inverting thing, where the bottom light went to the top and the top light went to the bottom, then you end up with something that's parallel. Well, you end up with it the wrong way. So I wouldn't bother with saying that. But anyway, so they're not really parallel lines. They're only parallel in the sense of the proportions of the size. Yeah. Okay. So where do I want to go with that? So anyway, this is the complex part. So anyway, so this is the part where I'm just saying, okay, so this is billions of light years this way, and it's billions this way. Okay. So yeah, all the angles get really small because you're going billions. You're taking this distance way far away. But the bottom line is you're converging photons on this clump, and this clump is maybe 100 million light years, or let's just say 10 for the sake of making it big, but not too big. I mean, it's a huge amount of space, and you'd have to have incredibly weak gravity for there to be any linearity. So your curve is, like again, the curve of this line is where it gets irrelevant. When the gravity starts getting really weak, then it doesn't really make a distance doesn't have much of effect. But a distance has a huge effect when you're starting off. So when you're right next to the thing, the gravity drops off rapidly and then goes to this weak curve. So this is incredibly weak gravity, and you still have to make an argument that you're going to be bending light in this incredibly weak gravity. And I'm still going to argue that you're doing it in the worst circumstance, whereas your galaxy is shaped this way. This is the shortest distance is this distance. This is the galaxy spoking out. So they're going through that shape. And if you wanted to get a lot of gravity, then you would go this way, along its side. Then you have a hope. So they have the galaxies angled the wrong way to be able to see anything. Well, anyways, look, my argument is this whole idea that you can, bend light is essentially saying you can give it 2 accelerations and then they'll take it away when it goes out of the well, which is all crap. You can't bend light. It's a force. None of the forces are bent by each other. None of them are moved by each other. It was just wrong-headed. So yes, there's some, there's some components here that you could add up and say, yes, we can make a lens out of this. But I'm saying that if you really analyze it and do the math, they can't. And part of the evidence that they can't is the fact that they had to invent dark matter to explain, to put enough gravity in these locations to create this lensing. So we know it's there because they couldn't explain where the gravity to bend the photons was sufficient. The gravity is not proportional in any kind of real sense. I mean, it seems kind of unlikely that you have just the right gravitational degrade, for the lens length, but maybe there's a way of figuring that out. Like at a certain lens, at a certain distance, the r squared thing works out. But again, it just wouldn't make sense that it would work out so perfectly that the lensed images are always of the same brightness. There's very little, it gets dimmer and then gets really bright. Very little fading on any of the lenses. They're all very sharp and consistently bright. And that doesn't seem reasonable at billions of light years of distance. You can sort of see that with a regular lens. I mean, you can be close to a focus, but it's not the focus just isn't good enough. And as soon as you get to that point, everything gets quite fuzzy. And these aren't fuzzy. The lens little shots are some of them have incredible amounts of detail in them. And that seems, and even detail on, across 100 light years or 10 light years of space, perfectly graduated, angularly perfect to get to us as a perfect image. So each angle is exactly the right angle on each photon, so that there's no degrade in the image quality. I don't think that obeys any kind of laws of probability. And what else do I want to say? Yeah, more work required. There's got to be a catch in here where I can, I thought I had a solid defeat in the sense that the gravity is going the wrong way. But like I said, you can get around that by not reversing the image. And but it's, like I say, you still got to account for this being enough light captured here that you're concentrating at this other end. And I don't know exactly the rule regarding how much area you need, how big a lens needs to be to resolve something at a distance. There's rules about that. Like even with our telescopes, there's a certain point where the point you can't see. There could be two things and they're going to look like one thing because you can't resolve them. And I think this breaks resolution rules. But I don't know enough of that math to do that. Well, anyway, more thought required. But clearly, you can't apply, electromagnetic charge. You can't apply charge electric equations to gravity. The electric force is one of the biggest numbers in the known universe, stronger than the gravitational force. So that's cheating. And electricity isn't a mass issue. The mass of the charge is irrelevant. The only thing that matters is the charge on the charge. And charge can be held on cellophane. Charge doesn't care about the mass. It cares about the surface area. And so they're completely different models. And you can't use math from one on the other. You can only use derivatives of the math. And so that's just wrong. Derivatives mean things like the r squared rule. Alright. So I thought I had another lensing point to make, but I think that's probably enough until I learn more about not only the density of the crap in the way, but how much gravity they're claiming is bending the light enough to create an angle that can be resolved over 1 billion light years. And if they're saying that weak gravity can bend light enough, then the consequence of that is that all the stuff the light's passing for the billions of years it has to travel to get to the lens is going to be bending each photon very differently, because the fields they're going to be in, the gravitational fields, are going to be different because they're far enough apart where they won't have any similar. Again, if I make this screen really big, miles and miles wide, you can sort of get the idea that the bits will be far enough apart that something that happens to this pixel won't be the same as what happens to the pixel over here anymore. They're going to be going through different fields in the space, and they're going to be affected very differently, and that's going to just wipe out this resolution. Alright, probably enough. So yeah, I think I explained the whole force dynamics with a little space shuttle example and different things. Force is something has to have, and there's no way for a photon to hold force in any other direction. You have to possess the force of velocity. You have to collect a force. Photons can't collect force in any direction but the direction they're going. And I think that argument is just so rock solid. There's no mechanism for it to hold momentum in two dimensions. Okay, enough said.